All right, let's move into the very last chapter that we need to cover for this semester. It's called Turbomachinery. It's basically equipment that interacts with flowing fluids. And you can lump it into a thing called pump, things called turbines, and then things that connect pumps with other components. Let's just say put a pump in a system or a turbine in a system. A pump is some device that imparts energy to the fluid. Energy to the fluid. And we know about the mechanical energy of the fluid, right? So typically a pump boosts the mechanical energy of the fluid by increasing its pressure. And so now pump has a connotation of being with the liquid. You could also have a compressor. You could also have a fan. You could also have a blower. Those are terms that impart energy to fluids. A fan and a blower and a compressor all are like gases. The compressor is a higher pressure. A fan really doesn't boost the pressure, but it boosts the speed. And the blower is one where you're having a lot of flow at low pressure. It's really a low pressure boost, but it generates a lot of flow for the blower. Okay, turbines. Turbines, it could be gas turbines, hydraulic turbines with liquids, but basically the purpose of the turbine is to get energy from the fluid. So the fluid can be a liquid, can be a gas, but you want to get energy out to turn a shaft. So pumps and fans and blowers, compressors typically are driven by a shaft, and turbines are driving a shaft. Again, the system is where you hook a pump up into a system. Here's a picture of a pump. This is what we call a centrifugal pump. This is the vast majority of water pumps. They are radial flow centrifugal pumps. This is electric line coming over, it drives electric motor. The electric motor has a shaft that drives this pump. Right here is the pump section, looking at it sideways. There's a pipe that brings water and a pipe that takes water away. Okay, so we know that the electric power is going to come in, and if it's a single phase driving that electric motor, it'd be something like E times I times PF. So the RMS, root mean square electromotive force, like voltage, or the RMS, the root mean square of the current, times if you have a power factor for that motor. And all motors are induction motors. They do have a power factor with it. If it's three-phase, you have that square root of 3, and then similarly the power factor. But this would be the power into the motor. Well, only a fraction of that gets converted into the shaft power, true? And so that's our efficiency of the motor. So the shaft power, then not all of that mechanical power is converted into the fluid power, just a fraction associated with the efficiency of the pump. All right? So where does the 1 minus the efficiency of the motor times the power, electric power coming into the motor go? If only eta of motor goes into the shaft, where's this go? This goes into heat. And a lot of times they have little fins on the motors, and if you go see a motor, you can sense it. It's warm and hot, and they have even air places for a fan at the end of the motor, bring air in and cool it off. All right. Then also, where does this 1 minus the pump efficiency times W dot shaft, where does that go? Well, it basically goes into beating up like an egg beater for the water. So this gets into the water. Typically, this is into the air. And typically, the water flow rate and the specific heats are so large, you really can't measure a delta T of the water. The temperature difference is so small. Okay. Well, which one of these pipes is the inlet? The one that comes into the middle of that round circular centrifugal water pump. If we took and looked at it on the side, that is where the inlet pipe is connected, comes in there. And then the discharge would be something over on the side, like this. This would be the out. Okay. So what are the main parts of a centrifugal pump? We have the eye region, that inner region where the flow is coming in, and then it's going to turn 90 degrees and go into an impeller region. So this is the eye there, and then the impeller has a sequence of blades that look like that. They can be very radial, or they can be curved like that. On a very cheap water pump, you can go to Home Depot, get one for your fish tank or aquarium, the dirt cheapest water pump. They'll typically be radial. And actually, you're running it off of alternating current. And if my memory is correct, some of those motors, it depends on how it starts. It would twirl one way or it could twirl the other way just as easy on really cheap low-end pumps. And when they're radial, it doesn't matter. It's just going to throw it out, and the radial pumps work. But if you have to know that it's going to be rotating this way, you're making sure it rotates that way from the motor, then the blades typically cut into the eye to bring it into this impeller region, and they throw it out, and it slides along, so it has some relative speed along the tips, and then it also has that tangential speed there, and then you have a vector diagram to get the composite speed of the water coming off of the tips of the impeller. From Euler's equation, when we studied the angular momentum, you find that you have to supply some torque to that rotating impeller in order to increase the angular momentum of the water coming out of the impeller. Usually the water coming into the impeller has zero angular momentum. Remember that? Good. The casing is the region which collects up the water, and usually it's small or close to the outside impeller, and then it grows in size and grows in size and then does something like this. I drew it kind of sloppy. There's a pinch point right in there. And that collects up more and more water. And that's a very important region, that volute region, because what you're doing is it comes off of the impeller at very, very high speed. This is the maximum speed. But it's not going out the pipe at that speed. So it's going to be slowing down in that volute region, that casing region. And as it slows down from Bernoulli, builds up pressure. It converts that kinetic energy into head. So that's the basics of a centrifugal pump. Let's talk about performance of a centrifugal pump. Think about having a water tank, and it's supplied to some meters so we can measure flow. We're going to have to measure the rate at which water is coming out of that tank into the piping system. Put a valve just so we can isolate if we need, and put it into the pump. And then out of the pump, we'll have a valve as well, another valve. And then from it, we'll just have a free discharge into a very large tank and collect on the bottom. So these are the basic setup. So when this pump is running, you can measure the flow rate. That would be AV, the volumetric flow rate. Or if you wanted to do the mass flow rate, that would be rho AV. True? So that's what the flow meter measures. The head is going to be measured if I put a tap right here and put a pressure gauge, and put a tap right there and put a pressure gauge. And so it's going to be able to measure the pressure inlet to the pump and maybe the pressure outlet to the pump. And that pressure head would be the pressure difference, delta P, across the pump. Sometimes they'll just say it's the pressure gain across the pump. Okay? Sometimes they'll just report it as head in units of feet or meters. Well, we have learned how to convert between pressure, delta P, and head. So if you were given the pressure difference, how would you get the head, delta P? What would you do? Divide by the rho G. You would divide by gamma. Gamma is rho G. What is the name of gamma? Weight density. Weight density, right? It's the weight density. So, okay, sometimes they'll also put it in cap H, little different head. That head is energy per unit mass. Well, you can jump always between these things. So it's delta P divided by what? Rho? Isn't it? If this is energy per... So I know that a lot of times we talk head, and we talk head in units of feet or meters. But sometimes you'll see a plot of pump performance and its energy per unit mass, or its pressure. Okay. This is the water power. What is the water power? So in this system, we are measuring the flow rate. We know the flow rate. We know the delta P across the pump. Well, that's what successfully went into increasing the mechanical flow energy of the water. Isn't that W dot F equal to delta P times AV? Is that true? What happens if somebody says, I give you head instead of a pressure gain? That's going to be head times rho G or gamma times AV. We have to make sure to be confident and we can do those calculations back and forth. But the water power, that's the power that's actually getting where you want it to go. The pump is getting it into the fluid. It's realized by the change in pressure or the change in head, either one, and the flow rate, either the volumetric flow rate or this is kind of a funny flow rate, a weight flow rate, right? Because that gamma is weight density. All right. Well, there's power to drive the pump. What is the shaft power or the brake power used to drive the pump? W dot shaft. Okay, how do I calculate W dot shaft? It would be the product of the turning rate, the omega of the shaft, that's in radians per second, and tau, the torque in the shaft, true? So that would give us the shaft power. And we know the shaft power is going to be greater than the fluid power, and the ratio is the efficiency. So the efficiency right here, I'm running out of room. Let's say the efficiency of the pump is the W dot that gets where you want it to go into the fluid divided by W dot shaft that has to drive the pump. That's the efficiency. Now, you open this valve completely, and it's a very short section of pipe. This is atmospheric pressure right here. You really are driving the flow. Maybe you don't really want to have a high hydrostatic head to really, the pump doesn't do anything but get in the way. But just have plenty of flow, and the elevation of the water in this tank here, it's not really driving it. The pump is what's driving it. And what you can do is, by having this completely open, is you can get the free capacity of the pump. The pump can only help so much fluid through it. And then, if you wanted more fluid to go through it, you would have to sort of build up pressure and push it through the pump. But that would be the free flow capacity. When you had it like that, the difference in the pressure would be nothing. P2 would be equal to P1. It's just throwing the fluid through. It's not boosting the pressure of the fluid. Okay. The next thing to do is shut this valve off. Close this valve. Okay, if you completely close the valve, what do you think P2 is going to do? It's going to go up. It's going to go up a lot. But what's the flow meter going to say? I have no flow through it. And that's going to be then the shut-off head. So we have two extremes on the performance of the pump. We have the free capacity, and we have the shut-off head. What we can do is put the data into a plot and do a pump performance curve. I'm going to try to put the plot somewhere. I need to scroll down a little bit. Let me put it right here. On the plot for the pump performance curve, we put on the x-axis the flow rate. Typically the flow rate's volumetric flow rate. Maybe it's meters cubed per second. Maybe it's GPM, gallons per minute. And on the y-axis we put the head. What do you mean the head? That's the head developed by the pump. Either we put it in meters. Sometimes they'll put head and then they'll put it in kilopascal. Okay, they're using head loosely. It's pressure head, but that head. So one point is the free capacity, where you just have open flow. It's as much as can go through. You're never going to get as much flow through that pump ever again. But that pump generated no head. That's why it's at this point. It's on the y-axis. The x-axis. The next point is the shut-off head. That point is on the y-axis. What we have is we have no flow, zero flow, and we have the maximum head possible. In between, you would experimentally measure, and typical pump performance curve would look like this. Maybe draw it again. It'd look like this. It'd be steep on one side and pretty flat on the other side. And for every point of operation, I can calculate the efficiency of the pump. So we would measure the shaft power coming into the pump, and then we'd also measure what went into the efficiency of the pump, what went into the fluid, which would be the head gain times rho G AV, something like that. Wouldn't that give me a good indication? It would be a product essentially of the head gain and the volumetric flow rate to get the power that went into the fluid. And you would divide that by the shaft power to drive the pump. That gives you the efficiency. So what is the efficiency at the free capacity? 0%. Why is it 0? Because the head gain is 0. What is the efficiency at the shut-off head? 0%. Why? Not because the head is 0, but this time because the volumetric flow rate is 0. And so maybe it jumps to 20%. Maybe it's 40% efficiency. Maybe it's 60%. Maybe it's 75%. But you know what? It goes back to 60%. And then maybe it goes back to 40%. And then maybe 30%, and maybe 20%, and 10%, and 10%, or something like that, or 9%, or something. You know what I'm doing? So along that curve, that's our performance curve, you could identify the point of operation which would give you the best efficiency. Don't you love this about mechanical engineering? It's just all so straightforward and simple. It's like the mechanical engineers that work with pumps, it's like straightforward. It's like that's the best efficiency point right here. It's where you get the highest efficiency. How would you determine it? Typically, experiments. You have your pump and you design your impeller and you go out and measure it. Now, a lot of times the company will have a casing that's the standard casing. And it used to be where you could buy different size impellers to go inside the same casing. This is a little old school because they used to put on a motor, and the motor ran at 1200 or 1800 or whatever RPM, 900 RPM that motor ran at, or 3600 RPM, and that was it. That motor wanted to run at that RPM. It tried to run at that RPM. There's a little slip, so it always runs a little bit lower RPM than its designated speed. But you would then, if you needed to, affect the performance of the pump in the system, you would change out impellers to get it optimized. Well, right now with the electronics, that's all changed in the last 15 years. They simply put the one impeller that gives you the best efficiency, typically the largest impeller, inside the casing. And then they put what they call a variable frequency drive or a variable speed drive on that motor, and they slow that motor down by changing the voltage amperage to the motor. Actually, I'm sorry, the voltage frequency combination, which then dictates the amperage to the motor. Really slick, really slick. The VFDs save a lot of money. And nobody puts out any pump anymore without a VFD driving the motor on it. Or I should say, I don't know of any real applications where they don't put them on. They even have VFDs on the fan of your new compressor in your residential air conditioner. Refrigerators too?
Refrigerators too? Open coils anymore. Now they get a little condenser with a little fan in there.
Do they?
Keep it clean because you know there's a lot of debris behind your fridge.
That's the problem with high efficiency. If you have a little degradation because of lint and other things, performance plummets. So yeah, in the refrigerators, I haven't seen that personally yet.
They want big coils.
They want big coils? Yeah.
They don't want small coils with a fan on them.
Yeah. So you change out the impeller. Now that I've described different diameter impellers, let's take a look at a pump curves from a manufacturer. This is an actual manufacturer, Teco, and they sell these pumps. This is their model, whatever model it is. And it's designed to run at a motor that's supposed to give out 1,200 RPM, but usually the motors have a little slip, so they don't give it 1,200, it's 1,160 RPM. And they tell you the minimum impeller diameter is 8.3 inches. And from the sequence of curves, you can look and see that here's a curve that is for 11.3 inch diameter impeller. This is the 11-inch diameter impeller. This is the 10-inch diameter impeller. This is the 9-inch impeller. And the 8.3-inch impeller. Don't go lower than that. It's ridiculous. Okay. So they have these impellers. That would be the maximum and down. Notice I forgot. Slow introduction. What's on the x-axis? Flow rate and GPM. Okay. What's on the y-axis? Head and feet. And I'd always throw students that have never taken fluid mechanics for a loop. It's like, huh? Head and feet. But you are masters now, right? You know this. Don't get too confused. So now, there's a lot of information on these curves. So these are different impeller diameters. Notice they don't extrapolate this all the way down, do they? Why don't they do that? Don't operate in those vicinities. Just don't even think of it. And they typically extrapolate these curves over beyond, like, say, 50% efficiency just because they want to put their numbers to tell you how big the impeller is and maybe the deadhead pressure or the deadhead head, okay, the cutoff head. But otherwise, don't even try and operate. Like, do not operate out in here and do not operate out in there, okay? So where do you want to operate? Well, these are lines of constant efficiency. That's an 84% efficient. This line at 83% efficient. So first of all, that pump, even the best, is around 84%. It's not going to be more efficient than that. But you want to operate that pump kind of in this vicinity. And the closer to the sweet spot, the better. Now, it's kind of funny, but once you pick let's say I picked a 10-inch impeller and installed it, I'm just going to operate only on that line. I put a zone out there, but really it's only going to operate along that line with a 10-inch impeller. Okay. So it would be able to go in the range of this type of flow rate, let's say 700 GPM down to maybe 250 GPM. And when it was producing 700, it would put out about 30 feet of head and maybe around 46 or 47 foot of head right there. Okay? That's it for this pump. You can't wish it to behave differently. this is the reality that the engineer has to deal with. So when you size and select pumps, this is what the engineer looks at. Okay. This is, if you want to work in SI, they convert it over to head and meters, and right up here is liters per second. So this is the SI side, that's the US side. Okay. Let me kind of give you some more information on this. What are these numbers right here? The size 5 by 6 by 11 and a quarter. It's typically they have two diameters, and then the other is that maximum impeller. It looks like they're rating it 11.3 is 11 and 11.25. It's close enough to 11.3. So the numbers typically are two diameters, the discharge, the inlet, and then the impeller diameter. You have to check on the naming things, but typically they're close to the same diameter, the inlet and the discharge, but the inlet pipe connected in the eye is usually a little larger diameter. We'll talk about problems with cavitation in a minute, but they want to avoid cavitation problems. All right. Question: would this pump be a good match to operate at 500 gallons per minute at a capacity of 40 heads? So the capacity is 500 GPM and the head is 40 foot, yes or no? So yeah, you would go out and say 500. 500 somewhere along here at 40 foot of head, somewhere around there. Actually, that would be great. You'd like that. Let's take a look at the next one. 500 GPM, 65 foot of head. And what happens is that pump, you can wish it all day long. It's not going to happen. It's not going to happen. Okay? If you specified that pump as an engineer and then the performance of the system was not up to par, then they have this fix. And somebody usually has to pay for the fix. And hopefully it's not you. 200 GPM and 20 foot. 200 and 20. Nope, don't use that pump. And 700 GPM at 35. 700, 35, it would work. It would work. Okay, so 2 yeses, 2 nos. Now, a lot of manufacturers put together, this is still a little bit old school, used to have catalogs, printed things like printed newspapers. They had catalogs and you could flip through and they would have either at the beginning or the back of the pump catalog a composite sequence. And these were always confusing, but let me just explain it. Each one of these little boxes like this is shaped like that's the best point for that model or range. And so I know they overlap, but if you're interested, this one here, it has a box like that. It maybe only shows this corner, but let's say this one, it has the same type of footprint, meaning that there's a couple different pumps which would work if you're kind of looking to go in that vicinity right there. So you could select this one, this one, this one, this one. They would match. But if you're trying to get right here and right here, well, it looks like this is the only one that would work out of that suite. Don't pick this one for sure. Okay, so that's why they have these little shaded areas on a composite curve. Notice this is typically they put it together for 50 hertz or 60 hertz. Why 50 hertz or 60 hertz? Anybody been in Europe? What's the standard alternating current frequency in Europe? 50 hertz. 50 hertz. Anybody try to bring electronics back and forth? No? Is that Germany? Middle East. Is it 50 hertz? Yes. And in different voltage as well, but definitely the frequency is 1. Okay. All right. So what do they have down here? They have flow capacity, meters cubed per hour or GPM. Good. They have head and feet or meters. That's good. And over here, if you're running with a 50 hertz, it's a little different sequence. These Gould pumps is a very international company. Okay, they're telling you the range around the best efficiency point, like 80 to 110% of the flow efficiency as well as of the head around the best efficiency point. That kind of gives you that map there for how big that box is. You really don't want below 80, well, 110%, to be too high a flow. Let's talk about this problem. A pump increases the head of water from 1.2 meters to 306 meters at a flow rate of 1 meter cubed per minute. The inlet and outlet pipe diameters are the same, and there is negligible change in elevation across the pump. Basically, the change in kinetic energy and the change in potential energy are zero. The pump efficiency is 77%. Determine the shaft power supplied to the pump. So we have the head coming in, head 1, 10.2 meters. The head going out, 306 meters. And a flow rate of, so the delta H, just calculate that right away. Yeah, it's 306 minus 10.2 meters. And the volumetric flow rate is 1 meter cubed per minute. And so determine the shaft power. W dot shaft is going to be 1 over the efficiency of the pump times what gets into the fluid. And so 1 over the 0.77. What about the power that gets into the fluid? That's the head change. You have the weight density and the volumetric flow rate. True? Maybe I should have worked that out, leave its symbols for a little bit longer. So 1 over 0.77. What is that? 306 minus 10.2 meters. What about the weight density of water? Yeah, 9.81 kilonewtons per meter cubed. And then you have 1 meter cubed per 60 seconds. So the meters cubed go. Kilonewton times a meter is a kilojoule. And then you divide by second, that's a kilowatt. $62.8 kilowatts. Make sense? Good. If we go back to our pump here, we can see something right in this vicinity. I'm sorry, but this is hard to read. But can you see what they're saying right in here? This is 10 brake horsepower. This is 7.5 brake horsepower. What are they saying? They're saying that motor that drives the shaft to this pump to deliver this sort of flow rate at that head, it needs this 7.5 brake horsepower or 5 brake horsepower. So if you buy this pump and you anticipate staying below this line, you only need to put a 7.5 brake horsepower motor on it. If you buy this pump and you anticipate always staying basically everywhere below it, it's a 10 horsepower. So if you buy that pump, don't put a 3 horsepower on it and then try and operate out in that vicinity. The motor will have major problems. And what will happen? The motor will try to do what it's asked to do. It'll try to maintain that speed. The amperage will go up and you'll burn out your windings. So it won't last long. So that's one other piece of information that incorporates the efficiency, this 70%, 74%. Okay. There's one other piece of information that's on here. Let me see if I can continue. It's the problem of cavitation. We were introduced to cavitation. Remember way back, first chapter, second chapter, all these concepts are thrown at you. And what was the problem with cavitation? in your own words? Anybody want to? It's very damaging to pumps, internally to pumps. And it's caused by saturation. It's caused by vapors forming or gases forming in your liquid, and then them little bubbles will form. They like to form in low pressure regions. And then when the fluid is swept with the bubbles to a high pressure region, what does the bubble like to do? Goes away. And it goes away and it creates a little ping, pop. And then that's a pressure pulse. And surfaces, it's like that high-low pressure that actually pops off metal to cause the erosion. So anyway, cavitation is a major problem in pumps. And so we know what it is, and now how do you avoid it? Well, you avoid it by not having low-pressure regions. And so what you can control on that black box of a pump is the pressure on the inlet. And so basically the pump manufacturers say you have to have a net positive suction head, a minimum, which is the requirement to avoid cavitation. So on the inlet, they have something net positive suction head, okay, and the manufacturer will say this is the minimum that is required. You need to make sure that what's available when it's running, the net positive suction head that's available is greater than net positive suction head required, and you're all okay. No problem with cavitation. But if the net positive suction head available when the pump is running is less than the net positive suction head reported by the manufacturer as what's required, you got a problem with cavitation. I know the subscripts and everything can be very confusing to you, okay? But this is what is required, and the manufacturer tells you, well, how do I calculate the net positive suction head? What exactly is it? Okay. Yeah. So what happens is you have the concept from Bernoulli that you have the pressure plus 1/2 rho v squared. That sum is something. What is that? That's the static plus our dynamic pressure. It's our total net head pressure. Okay, you want to do it in head? How do I convert that to H? Divide by rho g. That's exactly right. And so you have P divided by rho g, or sometimes just like H plus 1/2 v squared over g. Okay? So that is our head. And now that has to be above something. It has to be above. Let me get rid of this. I'm going to do it both in pressure and then in head. Okay, so pressure, it has to be above the saturation pressure of the fluid. The saturation pressure of the fluid is a function of temperature. And so this tells me, this equation right here is the net positive suction head in pressure. Now if I do it this way, I have negative P sat divided by rho g, it's a function of temperature, I guess I should emphasize that, is equal to the net positive suction head. This one's in feet or actual, what most people would call head.
So it just needs to be positive.
Well, no, it needs to be positive greater than the manufacturer's minimum to avoid cavitation. Yeah, that's a trick right there. That's a trick. So, so this is how you calculate it, either in pressure or in actual head. So, fluids that are cold, remember our pressure, temperature diagram going from the triple point to the critical point in thermodynamics? We have the saturation pressure, P sat, as a function of T. If you want to know the saturation pressure, come up, go across, read it off, go up, go across, read it off. What happens as I increase temperature? What's the trend? goes up. It's easy to get hot water to vaporize relative to cold water. It has a much higher saturation pressure. So this is more of an issue when you have warm water. When you have warm water. All right. I think let's go back to the plot, the tacho plot. Now finally we can understand this net positive suction head in feet. But where is that information? It's hard to see. But this right here is a line of 16. This is a 10. This is 6. This is 4. So what you're supposed to do is take those lines and just kind of extrapolate down. Okay? So if your pump is to be operating anywhere on this line, right here, 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 you need 4 feet of net positive suction head. That's what's required. You better have more than that available, or you're going to have cavitation. If you're operating the pump out in here, which would be pretty extreme, you might, to avoid cavitation, you have to have 16 feet of net positive suction head. So the manufacturer tells you the net positive suction head that's required to avoid cavitation, typically on a plot. Let me see if I have another one. No, that's just the same plot. I don't have any others. And then what you do is you check to what is available. So how do I avoid cavitation? Well, make sure I have sufficient pressure on the inlet. Pressure on the inlet. So let me try this one. Insert. Before I do that, let me get to the simple application. I think I probably mentioned it already. Here is a water tank, and it's your first day on the job, and you're expected to solve the problem of moving just a little bit of liquid out of this tank and pushing it over to that tank. And the engineer says, go out and solve the problem. You say, I'm going to lay a pipe. It's going to come out over here. And then the pipe is going to come up. And then I'm going to actually discharge like this so it just falls in to the tank. That sounds good. Where do I put the pump? Can I put the pump up here or put the pump down here? Always put the pumps low, because if you put the pump on the top of the second tank, what happens is it's got to draw that water up. And even if the pump's not running, what is the pressure in the pipe right there? It's the gas pressure in the tank, typically atmospheric pressure. And if you try to run this pump, it'll try and draw that water up by sucking it. And that pump will have a very hard time of actually getting it to go anyway. And if you did get it to go, it'd be very susceptible to cavitation. So guess what? Easy solution. Engineers put the pumps in the basement, not on the roof. Done. You go into a mechanical room. No, I want to go to the penthouse mechanical room where to see all your... No, that's all in the basement. Let's go to the basement, because pumps avoid cavitation that way. Okay. Let's solve one problem. Water at 30 kilopascal and 60 degrees C enter a pump in a 25 centimeter diameter pipe with a volumetric flow rate of 0.15 meter cube per second. Calculate the net positive suction head available at the pump inlet. So what's the net positive suction head available? It'll be, what units do we want this in? Do we want it in meters, or do we want it in Pascal or kilopascal? All depends. We could calculate it both ways and easily. Once you calculate meters, say, oh, I need it in kilopascal. Let me give it to you right now. It's easy, okay? So which way do you want to do? Meters. So it'll be the inlet static pressure divided by rho g of the fluid. It'll be the V squared over 2g, so I'm going to have to get the speed of the fluid. Often the speed of the fluid's negligible in the contribution to the total head, but we're doing it this way. And then you subtract off the saturation pressure. which is a function of temperature. Just to emphasize, if temperature is 60 degrees C, that's pretty warm water, and you divide by rho G. Okay? That's going to be the net positive suction head available. Now, some books put a big A, some books put a subscript A, some books put a subscript lowercase a. Hey, just whatever it is. Okay. So let's do the 30 kilopascal divided by 9.81 kilonewtons per meter cubed. And a pascal is Newton per meter squared. Okay, so the pascals go, the newtons go, the kilos go, and we're left with 1 meter for the units on that. Now, we have to do a little work on the side to get the velocity. It's the volumetric flow rate divided by the... Have you done enough of these calculations to really feel confident? You know, give me the volumetric flow rate, the diameter of the pipe, I'll give you the velocity, believe me. Not too hard, right? So 0.15 meter cubed per second divided by pi, 0.25 meters squared divided by 4. Somebody want to run that for me? What is that? 3.05 meters per second. Fine, we'll go. What's the fourth digit on that? 5 meters per second. Okay. 3.055 meters per second, square it divided by 2 times 9.81 meters per second squared. And so let's go ahead and run these as we're going. 30. So this is 3.06 plus 0.476 meters. Okay, what's the saturation pressure of water at 60 degrees C? All right, it's 19.94 kilopascal. 19.94 kilopascal. I'm just going to use, it's still 9.81 kilonewton per meter cubed, but I know that it's going to be slightly different. It's going to be a lower density, but I don't want to fool with that. So 19.94, 9.81 divide. So this is negative 2.03. So you we have 1 point. The net positive suction head available is 1.5 meter. All right. Thank you for your attention. We'll pick up there next time.